So we're going to continue talking about our gas laws and looking at problems with them. So we know that our model of understanding gases is one of the factors is that the particles are moving, and we want to look at how do if we change one variable, how that affects the change in another variable. So we are going to use some different strategies with understanding how to calculate for problems, okay? So for today, I want to look at our learning intentions is identify the mathematical relationships between our four variables that we've been using: volume, pressure, temperature, number of moles, our particles, and then apply that to a problem and solve for an unknown variable. So to be successful with this, I would say you should be able to set up the problem correctly and solve with no mathematical errors. Answers expressed in the correct sig figs. We've been working on that throughout the year. And be able to draw a model if I ask for one of what is happening with the container or inside the container with the gas. So some essential information that we need, and this would be given to you, is our pressure conversions, our equation for converting from our temperatures from Celsius to Kelvin. Remember, for gas laws, temperatures need to be in Kelvin. You cannot have them in degrees Celsius. It always has to be in Kelvin. We use the absolute scale. And then the other one would be standard conditions. To abbreviate that, in chemistry they'd say STP, and that means 1 atmosphere in 0 degrees Celsius. So I'm looking at a problem in our packet, and this is the problem that's given to you. So if we look at this problem, we should be able to solve for what the new volume will be. Okay? So in order to do this, we are going to use these PVnT tables, and these tables we're going to use to identify what is changing, what are they asking for, and then how to set up the ratios. Now, we have put in our variables that we know. So we know we start out with 150 milliliters for the initial volume. And we also know that the initial temperature is at, we're going to have to convert to Kelvin. It's 298 Kelvin. And the temperature is going to be raised to 323 Kelvin. Right? So I just took 273 plus the 50 degrees, I believe it is. Yes. And 273 plus the 23 degrees. Now, they want to know what is the new volume going to be. Now, some other things that were told to you in the problem was the fact that moles were held constant, and I'm just going to put a C there, and pressure was held constant for this. Okay? Now, I'm just going to do a little reference back to our gas laws. We had talked about gas laws prior to this, and remember when we did, this was Boyle's, it was the volume and the pressure. We saw that that was an inverse relationship. Remember when we did Charles, it was temperature and volume. We saw that that was a direct relationship. Then we did Gay-Lussac's. That one was temperature and pressure, and that was also another direct relationship. And then we did Avogadro's, which was the number of moles, or particles, to pressure, and that was also a direct relationship. So we need to keep in mind what happens when I increase the volume for here. If I increase volume, the pressure goes down. Really, Boyle's law, the first one, is the only one that was the inverse. All the rest of them were direct. So in this case here, where I have the effect, so I would look at this and go, hey, the temperature from here to here is going up. If the temperature goes up, what happens to the volume? Doesn't the volume also go up? So if it goes up, I'm going to set my ratio up like this. I need to get, my ratio has to be the ratio of the temperatures to get those to cancel out. So I want those to cancel because I want to know volume, and it's going to be in milliliters in this case. So I'm going to set up my ratio so that when I increase the temperature, the volume is going to go up, because I said if I'm doing this, this is the effect right here. So to do that, to set up my ratio of temperatures, wouldn't I have to put 323 in the numerator and 298 and the denominator. Notice my Kelvin should cancel. I do my calculation, and I get 162.5 milliliters. Now, I'm going to go to sig figs. If I went back to this, I think there was a decimal behind that. If I went back to this, there was 3 sig figs, and looks like it'd be 163 milliliters would be my answer. Okay? Now, the other thing would be this. I want to draw a picture to represent this. So I'm just going to draw a box. So if I initially had a box like this of 150 milliliters, I'm going to put some particles in there. And it looks like my volume got larger. So I'm going to exaggerate it and go, yeah, it's going to be larger. Okay? Notice, I held my particles constant. So how many particles I have in here? I'm going to have the same number of particles in here. Okay? The other thing is my temperature increased. So temperature we use with the vectors. If it's cooler, they're moving slower. So I'm going to put a smaller vector on those. If it's warmer, they're moving faster. So I'm going to exaggerate it just to show you that. Yes, there is a difference between the two. So that's how we would do a problem like that. So looking at a second problem here, this is problem number 4 on page 32 in your packet. It says, what would be the new volume if 250 centimeters cubed of gas in a sealed container at 25 degrees Celsius and 730 millimeters of mercury of pressure were changed to STP conditions? Now, so it looks like I'm changing temperature and pressure, so that means moles is going to be held constant. Okay? So we're going to identify which one is held constant. I'm going to go to my tables. When I go to my tables, I'm going to make sure that I fill out this is being held constant, so I do not need to deal with that in my equation. So then I'm going to put in the variables that I know initially. Initially, I have 250 centimeters cubed, and it looks like it's at a temperature of, I believe it's 25 degrees Celsius. I need to change that to Kelvin. That's 298 Kelvin. And the initial pressure is 730 millimeters of mercury. Yes. Okay. Now, it looks like the temperature is changing and the temperature is going down. It's going to be 273 because it's going down to STP, which is 0 degrees Celsius. So that's just 273 plus 0. And since the pressure is going to be 1 atmosphere, I have to be in like units here. And I know 1 atmosphere is 760 millimeters of mercury. I have to be in similar units because when I set up my ratios, I have to have canceling of units. Okay? Now if I look at this, I want to know what is going to be the new volume of this gas. Okay? So if I look at this, it looks like my pressure is going up. If pressure goes up, that makes the volume go down. That's Boyle's law, the inverse relationship. And the other one is, if temperature is going down, doesn't that also make my volume go down? Right? So in other words, the effect of these two different changes are going to make the volume decrease, and the other one will make the volume decrease. So if I'm going to set this up, I'm going to start with my volume, because that's what I want to solve for is volume. And I'm going to set up my ratios to make those effects decrease the volume. So to make that happen, I'm going to have to put the lesser number in the numerator. So it's going to be 730 millimeters of mercury over 760. And for the other one, it's going to be 273 over 298 Kelvin. Those will cancel. I do my math and I multiply through here. I got 219.9 centimeters cubed. If I go back and look at the problem for sig figs, it looks like it's 3, so I'd round that to 220, and I would include a decimal. I gotta look at that problem. Did I have 2 sig figs or 3? Oh, I only had 2 sig figs because there was not a decimal, so it would just be 220 centimeters cubed. Okay, so it looks like my volume decreased, so my container up here is going to be larger than what it is here. Okay, the number of moles inside my container is constant, so our particles, I'm going to stick with that 3, you don't need to draw so many. And then it looks like the other thing would be that the temperature decreased, so that must mean these ones have a longer vector, they're moving faster since they were warmer, and then these were cooler, so they're moving slower. So that would be an example of how to use those with the gas laws that we have studied, Boyle's, Charles, Avogadro's, and Gay-Lussac's. And that would conclude the lesson for today. So I was asking you to complete worksheets 3 and 4 and be ready for a quiz on Wednesday.